Hello friends, this is John Perham here again, and this is a small video about Fourier series, which I subtitled The Sound of Math because we can listen to them. So Fourier series are a useful technique for studying vibrations. Well, anyway, solid objects, springs, strings under tension, gases and mammalian eardrums all vibrate when subjected to forces. By vibrate we mean that some property of the system changes periodically. For example, a piano string when struck vibrates, causing pressure waves in the surrounding air to propagate. When these waves reach our eardrums, they cause the membrane to vibrate, exciting pressure-sensitive nerves to fire periodically, which causes our brain to register the original sound. Well, vibrations have got two properties: a frequency omega and an amplitude A. The frequency is the number of vibrations per second. The amplitude is a measure of the strength of the disturbance. In our previous studies we have met the periodic trigonometric functions sine of 2 pi omega t and cos of 2 pi omega t, which are both periodic with period 1 over omega. So anyway, here omega is the frequency, measured as the number of vibrations per second, which are designated in Hertz or Hz, named after the German physicist Heinrich Hertz. For example, a sound with frequency 450 Hertz, which is middle A, can be played for 2 seconds using this. So let's play it. It's not very exciting. We'll get rid of this guy. Anyway, so let's move on now to discuss periodic functions. Suppose we've got some function f of t defined on an interval 0 to capital T. Then we can define a t periodic function f of t to be equal to little f of t if t is in this interval, and it's equal to the same function f of mod t of t. So what is mod of t? Well, it's equal to t minus n times t, such that n is the largest interval or integer, such that this number is in the original interval. So there we go. So let's look at that. So an example of a suitable function is the triangular or sawtooth pulse, which can be defined using that. So f of t is the numerical value of 1 minus 2t over 2 little t over big T. So when t is 0, it's equal to 1, and when t is capital T, it's equal to minus 1. So we can define the periodic function using this, and we can plot this function for an interval like so. So we can see that this is the function in the primary interval, and we can see that it's copied, that this bit here is copied over to here and over to here and such. So it's a periodic function. And we can see from its shape that it's an even function, because this part of the curve is the mirror image of this part in the vertical axis. We can also see that the function is continuous. So this is a periodic function with period t, and it's tempting to believe that we can represent this periodic function by a Fourier series of the form a constant plus a sum over the integers of coefficients an and bn times respectively the cosine of 2 pi nt and sine 2 pi nt over t. This is clearly also capital T periodic. And this is a series that's called a Fourier series, and we'll explore its properties. Well, the first thing we notice is that since that if f of t is an even function, this is an even function, and this is an odd function. So if capital F of t is an even function, that must mean that all these coefficients must be 0. And likewise, if f of t is odd, then all the a's will vanish. So let's calculate the, and we should really correct that, that should be capital F. So let's do that. So how do we calculate the Fourier coefficients? Well, it's pretty easy to show that if we take one of these cosine functions and multiply it by a sine function and integrate over a period, then the result is 0, and we can check that using this piece of code, and indeed the result is 0. And likewise, if we now take a product of a cosine and a cosine with a different n, say m, or a sine, same thing with a sine, and if n is not equal to m, then that's also going to be 0. And we can check that for the cosines using that, 0. Now, that's true if m is different from m, and we can impose that condition by saying that m is greater than n, or either n is greater. Anyway, that doesn't matter. But the case when m and n are equal, we can calculate the corresponding integrals using that to be t over 2, and that to be t over 2 as well. Now, if n is 0, then the whole thing is a bit different. It's just the value of that integral will be t. So, in other words, these functions, when integrated over a period, have a kind of orthogonality property. So that enables us to easily find the coefficients, because if we multiply the Fourier series by either a cosine term or a sine term, then and integrate with respect to t over the interval, then we will find that the integral of ft with respect to t will be equal to this integral, and the only term which will survive will be the term when n equals m, and the result will therefore be this. So the result is that when n equals 0, or m equals 0, that a0 times t is equal to this integral, so a0 is equal to this. And if we take values of m different from 0, then we'll have that this integral here will be equal to the corresponding Fourier coefficient multiplied by t over 2. So this gives me a formula, gives us a formula for am. It's just this integral. And likewise, we'll find the same thing we do if we multiply it by sine, then almost everything drops out, and we'll just get the Fourier coefficient bm is equal to this integral here. So that's about all there is to it. Let's look at it for that triangular pulse we had above. We can look at that again here, and we can work out a0, the first the constant term, so it's 1 over t times the integral of the function from 0 to t over 2, this one here, and then we have to add the contribution from this bit, which is just here. So that gives us a 0, which is a half, and then we can use that to compute the other cosine coefficients, remembering that the b's will all be 0, and they're given by this this integral minus this integral, and we can easily do that, and we get this result here. And if we look at this, we can see that if m is even, then this term will be 1 and this will be minus 1, so we'll get 0. So in other words, these coefficients are 0 if m is odd, even. Or moreover, if we notice that the coefficients drop off like 1 on m squared, so that the Fourier series in this case will be convergent, because the term m, if we now take m equals 2k plus 1, which will always, for a k an integer, which will always be odd, then this is what we get. So we've got the odd coefficients look something like this, and the series will be convergent. So let's see how convergent it is. So let's take 3 terms in the series and plot the function. And we can see that that looks kind of like the original function. If we plot it, if we do for 5 terms, then we get that, and we can see that that looks even better. But anyway, if we superimpose the 3-term approximation on the original one, we can see the fit is kind of good. There's just a little bit of missing stuff here. And we can play, let's take the case where the period is 1 over 400, and we can play that, the 3-term approximation, using that. And we can play the 5-term approximation using this. Which sounds pretty much the same as this. So let's look at another triangular pulse. I'm going to define a function on the interval minus t over 2 to t over 2. And I want to specify its values at the endpoints. So I'm going to take a function which has this form here, and I'm going to choose it in such a way that when t is minus the period over 2, the value of the function is minus 3, and when it's equal to, when t is capital T over 2, then the function is 9. So, so we can get a couple of equations for a and b out of that, and we can set those equal to 0 and solve for a and b using that, and then we can define the, or redefine the function so that it has the correct properties, like so. And we can plot this function over for t equals capital T equals 4 using this. And there we go. It looks like that. Now if we look at this if we do the periodic extension of this, in other words, we copy this graph over to the interval from 2 to 6, then we'll see there will be a discontinuity here. But anyway, we don't need to do that to calculate the Fourier coefficients. We can calculate the A0s, 0 using this, which is just 3. And then we can calculate the other coefficients, cosine coefficients, using this. And they're all 0. And that's because the function here is 3, which is an even function, plus this, which is an odd function. So the only cosine terms will be A0. So now let's calculate the B coefficients. So we work out the integral, and there they are. And you can see that, as opposed to the previous example, that the coefficients are inversely proportional to m and not m squared. So let's plot the 5-term approximation, which is given by this. And you can see that this kind of looks a bit like the function in the principal region, but it converges much more slowly. We can take a 10-term approximation, and it's starting to look a bit better. And we can play the 5-term approximation for t equals 1 over 400 using this. Sounds kind of the same. Well, that's the end of the story. So let's stop the video, and there you go.